RMS Titanic is the most photographed and studied shipwreck in the world. It rests in huge, shattered sections, nearly 4,000 meters, that's 2.5 miles below the ocean. This footage was captured shortly after the ship had been first discovered in the mid-1980s, a time capsule resting in an alien environment. She'd been made by thousands of human hands, intended to serve faithfully for decades. Instead, she never made it to her intended destination, and nearly 1,500 lives were lost in the freezing North Atlantic. Titanic today is a rusted, collapsing hulk, a decaying empire home only to fish, crustaceans, and steel-eating bacteria. But, not that long ago, she'd been a brand new, shining example of just what humanity could achieve. We have always been the underdog in the quest to travel, to go places, and Titanic was the culmination of all the countless lessons we'd had to learn the hard way that nature could not, cannot be tamed. She was the finest ship afloat. But just how this ocean-going behemoth was meant to function, all the systems, the features that made her special, deserve focus to show just what an achievement the construction of ships like Titanic was in the age of steam. Ladies and gentlemen, I'm your friend, Mike Brady from Ocean Liner Designs, and this is how the Titanic worked. Early April 1912, and Titanic has just arrived at Southampton ready to take on coal and passengers for a maiden voyage. It had been a mad dash to the finish line to deliver the huge ship, and now she sat gleaming in the spring sunshine in a fresh coat of white, black, and gold paint. To the residents of Southampton, the sight of new ships was a familiar one, but Titanic and her sister Olympic were the biggest the port town had yet seen, and their towering smokestacks could be seen all across the city. Soon, Titanic would depart, her engines thumping to life, hundreds of passengers and crew aboard to set out for the new world. To understand how this mighty ship worked, we need to peel back the layers of steel to understand how she was built, because for the time, her construction had been absolutely cutting edge. Titanic was designed and built by an incredibly experienced team of engineers, builders, and artisans, and even though it was heralded as the world's largest ship, at the time, the Titanic was actually built in an almost identical manner to hundreds and hundreds of other ships. You see, Harland & Wolff, the shipbuilding firm that built Titanic in Belfast, had been building ships since 1861, and they were pretty damn good at it. In fact, they were up there as one of the best shipbuilding firms in the world. They were the builders of choice, not just for Titanic's owners, the White Star Line, but dozens of other shipping lines like P&O, Union Castle, Furness Bermuda, Royal Mail Line, and many more. But a long-standing agreement saw White Star Line commissioning virtually every one of their ships to be built by Harland & Wolff. One of the many stupid myths about the Titanic disaster is that Harland & Wolff was a cost-cutting organisation and built their ships out of substandard materials, and it's just not true. They'd been doing this for a long, long time, they knew their stuff, and they were extremely proud of their product. So when the White Star Line began discussing plans for a trio of superliners early in about 1907 or 1908, Harland & Wolff was all ears. They knew they'd have to overhaul their entire shipyard to accommodate the massive engineering task, so they knocked down all their old slipways and built a monstrous gantry to support cranes and build the new ships, as well as a cavernous graving dock to fit the ship out once it was afloat. Titanic and her two sisters, Olympic and Britannic, were not really that special. Yes, they were big, really big for the time, but Harland & Wolff wasn't going to reinvent the wheel on this project. They took what they had built on a smaller scale for ships like White Star's Oceanic, Laurentic and Adriatic, and they scaled the designs way up. So if you can understand how Olympic and Titanic were built, then you really know how almost every Harland & Wolff ship was built in the lead up to the 1920s. So when White Star Line began talking about advanced safety features for the new ships, Harland & Wolff was happy to oblige them, because up until only relatively recently, by then travel at sea was a bit of a gamble. Fairly regularly, ships were lost in storms and just never showed up. White Star Line cut its teeth on the run to Australia. That was a particularly dangerous route, and the worst 19th century loss of life in Australian waters happened after about 4 months at sea, when the sailing ship Cataraqui was just a day away from docking safely in Melbourne. So the travelling public was a bit apprehensive about travel at sea, and it certainly didn't help that in 1909 White Star Line lost a ship, the Republic, when it was rammed and sunk off Nantucket. White Star and Harland and Wolff would go above and beyond to make sure that Olympic and Titanic were as safe as possible. Safer, really, than any other ship afloat. And then they'd market the hell out of that fact. So what does this all have to do with the design? Well, let's take a look at how Titanic was built from the ground up. Titanic's hull basically formed a giant box girder. If you can picture it that way, then all the individual components will start to make sense. Box girders are immensely strong, and they are ideal for resisting torsion or twisting, which is very useful in ships because they are very long and prone to flexing and twisting while going over big waves at sea. Box girders require 4 walls to function. In Titanic's case, the bottom wall was the keel, the top wall was the strength deck at B deck, and the 2 side walls were the hull. Here's how it was built. First, the keel was laid. This is essentially the ship's backbone. It comprised a flat keel plate, which sat on top of the slipway's blocks, and then a girder, which ran most of the length of the ship. Then, along the length of the keel were fitted these things called floors. They provided something for more longitudinal girders to be riveted to alongside the keel. And slowly, the width of the structure increased until you had an immensely strong steel skeleton. The bottom of this was plated, and these steel plates basically formed a watertight skin for the ship. They were made of steel and were surprisingly thin. On Titanic, the plates ranged from 0.64 of an inch, or 1.6 centimeters, to about 1.25 inches at their thickest, which was 3 centimeters. The bottom of the Titanic, under the keel, was where the heaviest plates were used. Those were the big 1.25-inch plates I just mentioned. Now, on earlier ships, this is kind of where the yard would move on to the next step, but by Titanic's day, things had developed a bit and the ship was given a double bottom. This basically involved riveting a second watertight skin of plates on top of the keel structure. The deck that was created from this was called the tank top, and for good reason, because the space in between the plates on the bottom of the keel and the plates on top at the tank top was subdivided into tanks for ballast and salt water. The reasoning for this was simple. Ships, for as long as they had existed, had been bumping into things, so there was a lot of knowledge around the kind of damage a ship was likely to encounter. Grounding damage was some of the most common and the worst. In fact, the Costa Concordia kind of fell victim to this as late as 2012. If Titanic encountered shallow rocks or something that could pierce the bottom plating and open the ship's hull up to the ocean, it would sink quickly. The second layer of plating on top of the tank top would prevent this from happening. Crucially though, this second row of plating ended there. It did not continue up the sides of Titanic's hull, but we'll get into that in a minute. Next to the floors were riveted giant frames, which began to form the hull. These were the side walls of the box girder. These were forged steel beasts, multiple stories tall, bent into the correct shape to give Titanic's hull its streamlined hydrodynamic form, and they ran the length of Titanic's hull, spaced out every 24 to 33 inches depending on their location. To these frames were riveted the majority of the Titanic's hull plates, basically the external skin of the ship. From here up, the plates, which weren't part of the double bottom, were a little bit thinner. This was to save a bit of weight and to give the ship greater flexibility while rocking and rolling through a storm. Each plate had rows of rivets hand-driven into each edge, holding them all together. The rivets were wrought iron, pushed red hot into place and then hammered home until they fastened 2 plates together. 3 million rivets were used to construct Titanic's hull, and every single plate edge was dotted with dozens of them. If you were standing in the Titanic's boiler or engine room, way down at the bottom of the ship, you'd be standing on top of the tank top. Looking to the side, you'd see the big frames just where they curve downwards to join the keel and its floors, and then you'd see the plates. There is nothing between those plates and the ocean on the other side. There's not a second layer or inner skin or anything like that. Finally, to give the box girder its roof, the reinforced strength deck, which on Titanic sat as high as B deck, was riveted into place and all the subsequent decks below it. Remember when I said Titanic's hull was a box girder? Well, here is an actual box girder design, a cross-section of the tubular Britannia Bridge. Looks familiar, right? Okay, so Harland and Wolff now have the hulk of a ship. At the moment, it's safe from damage to the bottom in, say, a grounding. But what if the ship's hit from the side? An impact from a collision from the side would mean that water could flood the hull and sink the ship in minutes. No, something had to be done to prevent this, but it kind of seems incredible that the idea of watertight compartments was kind of revolutionary. For hundreds of years, ships had just sailed around without them. But Titanic took the idea to the next level. Titanic's hull was divided into 16 watertight compartments, basically massive self-contained rooms, by 15 bulkheads, which were essentially heavy-duty steel walls that ran up the hull as high as practicable. These were made of steel plating and of course ran through some passenger and crew areas in the lower decks. This meant that to get through them there had to be some kind of doorway fitted that could be sealed up in the case of an emergency. On Titanic, this came in the form of the watertight door, and the ship had a couple of different types. First is probably the most famous, seen here dramatically closing in the 1997 movie Titanic. These ran on rails and closed downwards. They were made of heavy cast iron, and in the boiler and engine rooms had to be wide enough for men to be able to pass through with coal-carrying wheelbarrows. The doors were held open by a clutch, and this could be released automatically by switches in the bridge, or individually by simply lifting a hand lever connected to the clutch. Each door could also be closed manually by hand cranking it shut from the deck above. And one final safeguard was installed. In the event of flooding, a float would raise the lever and disengage the clutch, lowering the door. The doors were designed to lower slowly at first so men could get out of the way, but for the last 18 or 24 inches, the door would drop suddenly like a guillotine to create a watertight seal. This guy in the movie would have been in big trouble. The second kind of watertight door closed horizontally, or laterally, and these were the ones found in most of the passenger and crew areas on Titanic's lower decks. These had to be manually hand-cranked shut, either on site or from the deck above. The watertight bulkheads had as few openings as possible, and when the doors were shut, created a compartment with 4 watertight surfaces: the tank top, the hull sides, and the 2 watertight bulkheads at either end. However, there was no watertight top surface. The decks above weren't made watertight because the bulkheads rose fairly high up in Titanic's hull above the normal waterline up here on E deck. With this system in place, Titanic could survive a number of theoretical disasters. If hit by another ship from the side, 2 or 3 of the Titanic's compartments would flood, but the ship could float, because the water could only flood about as high as the top of the watertight bulkheads. If the ship received damage to the first 3 or even 4 of her watertight compartments, say in some kind of sideswipe collision or impact, then the water also could not flood any higher than E deck, because the ship would find equilibrium, the flooding would stop, and the ship would survive, although its bow would be pretty low down in the water. Basically, Titanic was designed to withstand any and all the kind of damage that ships had experienced up until that point. Bow-on collisions, groundings, impacts from the side, Titanic could survive them all. She was almost, what's a good word here? Unsinkable? Unsinkable. Yeah, that's a good one. Let's use that. Titanic's builders had completed a huge undertaking, and it had involved years of preparation and planning. Probably the most heart-stopping moment for any shipyard are the sea trials before the delivery, the moment the ship must prove itself worthy of acceptance. Working her engines up to full power for the very first time, Titanic had carved her way through Belfast Lock, but manoeuvring such an immense vessel was no mean feat. A system of impressive machines had to be devised and installed just to turn the ship, and it was all because of her immense size. Displacing 52,000 tons and boasting an 892 foot or 269 metre length. When you have something that big at speed in the water though, it becomes very difficult to control and make it go where you want it to. Steering a ship accurately is hugely important to avoid collisions and make sure you're exactly where you need to be along your journey. So just how do you turn a 50,000 ton giant in an era before advanced electronics and computer systems? Titanic's steering system was made up of some key components. First, the rudder at the very stern or the back of the ship, connected to and powered by the steering engines directly above it. Then, 3 steering positions connected to the steering engines could direct the ship and make changes to its course using the rudder. Here's how it all worked. We'll start with the rudder. Most ships are turned using a rudder and have been for centuries. The rudder is essentially a broad, flat surface fastened to the exterior and swung left or right to turn the ship. There are a lot of different kinds of rudder which grant different benefits, and for the longest time, sailing ships had used simple pintle and gudgeon rudders which swung along their front edge. In 1843, the famous engineer Isambard Kingdom Brunel introduced the balanced rudder, which swung from an axis behind its front edge. Titanic's Cunard Line competitors, the Lusitania and Mauretania, used balanced rudders, but Titanic's rudder was different. It was a simpler pintle and gudgeon unbalanced rudder. The thing was enormous. It stood 78 feet or 24 meters tall, about the height of a 7-story apartment building, and by itself, it weighed 101.25 tons. The immense weight was thanks to its heavy construction. In modern ships, the rudder is usually hollow, but Titanic's huge rudder was made up of 5 massive, solid, mild steel casted sections coupled together by strong bolt flanges with forged bolts 2 to 3.5 inches, or almost 9 centimeters in diameter, holding them all together. The bolts were then buried in Portland cement, which was sculpted to hydrodynamically flow into the rudder sections and reducing corrosion by seawater thanks to the turbulence along those big bolt heads and reducing the overall drag. At the top of that rudder was a huge stock made up of forged steel and turned on a truly epic metal lathe in the machine shop. This was attached to the topmost rudder section with the same flange and bolt arrangement and the usual cement applied. Securing this enormous assembly to the ship was no easy task, and 7 nickel steel pintles and corresponding gudgeons held its huge 101-ton weight and gave it the required axis for turning. Cast into the gudgeons attached to the ship's hull were 2 rudder stoppers, which would prevent the rudder from swinging wildly out of control on either side. This limited the turning angle of Titanic's rudder to 40 degrees. Any further swing could create massive and sudden drag, damaging the ship's turning machinery and possibly shearing the rudder off entirely. Remarkably, the entire rudder assembly could be lifted up and removed from the ship for repair using pulleys and cables, thanks to a series of pad eyes which were cast outside on the ship's stern. These pad eyes were strategically placed in line with the rudder, as well as the ship's propellers, so that repairs or replacements could be made in dry dock. Lusitania and Mauretania's balanced rudders were cutting edge, and more in line with what would be found on warships of the day. Thanks to the balanced rudder's hydrodynamics, it meant that steering could be performed with less effort. Lusitania and Mauretania, thanks to their stern shape and the number of their propellers, could use a balanced rudder, but Titanic's design meant that a huge, heavy, unbalanced rudder would be needed instead, and it required an enormous amount of effort to swing it over. And this is where the second steering system came into play, the steering engine. Viewed from outside, Titanic's rudder stock disappeared into a hole at the base of the counterstern and the stern post. It ran a deck or 2 up until it reappeared inside a special room at the very back of the ship, on C deck. This was the most rearward located compartment on the ship, behind the third-class smoking and general rooms, and on the outside in photographs you can see it here. In the old days, ship's rudders were turned by a series of rope pulleys connected to the ship's wheels, but no rope could hope to turn a 7-story, 101-ton steel rudder like that on Titanic, so some pretty serious machinery would be needed, and there was no other option but the steam engine. Steam engines can create enormous amounts of torque, or rotational force, and in Titanic's case, one would be needed to turn the ship's giant rudder. The engine had its work cut out for it, because not only did the rudder weigh over 100 tons, but as the angle of turn grew larger, so too would the pressure of water flowing over the rudder increase. Titanic's steering engine and gear was actually designed and made by the ship's builders, Harland and Wolff, and featured 2 steam engines, with one serving as a backup. The 3-cylinder steam engine would respond to commands from the ship's steering wheels, or helms, and its 3 pistons would turn a crankshaft clockwise or counterclockwise as necessary. This would in turn drive large toothed gears connected by their teeth to a massive steering quadrant, so called because it resembled a quarter of a circle. The quadrant would then turn left or right, but it couldn't be connected to the rudder directly because this could put enormous strain on the engines and gear teeth and result in their damage or destruction. Instead, tiller arms, which were essentially big levers, were connected to the quadrant by heavy-duty spring coils so that they could absorb shocks or bumps in their operation and reduce overall stress on the steering gear. The tillers connected directly to the top of the rudder stock so that the steering engines turning the quadrant left or right would then mechanically turn the rudder in the required direction. If in the worst case scenario the whole thing stopped working, those tiller arms could be operated manually by connecting heavy ropes to nearby steam capstans, which were usually only used for tying the ship up in port. So the gargantuan rudder was steered by mechanical means, by steam engines and heavy-duty gears. But just how could a single man control this machinery by using a ship's wheel? Now this brings us to the final aspect of Titanic's steering system, the ship's wheels. The ship actually had 3 steering positions. 2 of them were forward, far away from the steering engines in the bridge. The first wheel was located in the navigating bridge, flanked by telegraphs which could ring down orders to the engine rooms. And behind this was the main ship's wheel, kept safely inside a special, dedicated room known as the wheelhouse. The third and final steering location was way aft at the back of the ship, on top of a structure called the docking bridge, directly above the steering engine room. And here is how the ship's wheels worked. It may seem unusual to have two ship's wheels in the bridge, especially when you consider that the main ship's wheel was in a room with very limited visibility forward. The fact is, though, that for the majority of the ship's time at sea, very few steering orders are required to stay on course, so the main wheel doesn't need to be in a position where visibility is important. To this end, protecting the wheel from the elements and potential damage from monstrous waves and storms isn't such a bad idea, and the sailor operating the wheel, known as the helmsman, would be responding to orders from officers on the bridge who could actually see what was ahead. The wheel outside the wheelhouse was far more useful when frequent steering changes were necessary. This included coming into port or maneuvering in dangerous or shallow waters. Typically, before Titanic entered a port, a small boat would come out to meet it, carrying a harbour pilot, a specialist with expert knowledge of the area who could guide the ship in safely using that wheel and its excellent visibility. So just how do you connect these ship's wheels to a steam engine located hundreds and hundreds of feet away at the stern of the ship? Ropes and cables just couldn't handle it. So instead, a technologically advanced machine called a telemotor was employed to respond to inputs on the ship's wheel and send those back to the steering engines, turning the rudder. The telemotor was a very clever device. It was located in the wheelhouse directly in front of the main ship's wheel and comprised a few basic elements. It was essentially an early type of servo motor, and it employed a cylinder in the wheelhouse and then a corresponding matching cylinder all the way back at the steering engine. Connecting these were hydraulic pipes containing a fluid mixture of 70% water and 30% glycerin to prevent freezing. Turning the ship's wheel left or right would push the wheelhouse's telemotor cylinder, forcing liquid through the pressurized pipes and pushing the corresponding cylinder at the other end of the ship connected to the steering engine. Springs inside the telemotor cylinder would give feedback to the helmsman, meaning that as the turn became tighter and he turned the wheel more in one direction, it would require more force to turn the ship's wheel. If the helmsman released his grip on the ship's wheel, then the springs would return it to a neutral position and the cylinders would return the rudder to amidships. All of this would engage the ship's steering engine, turning the quadrant and the tiller, and therefore the ship's rudder. Because of this system, one man could turn a 101-ton rudder with relative ease. The navigating bridge wheel was connected to the telemotor as well, and control could be alternated between either wheel as required. The third and final ship's wheel at the very back on the docking bridge didn't use a telemotor connection because it was located directly on top of the steering gear room. Instead, it was connected directly and mechanically to the steering engines. This gives us a bit of a clue as to its function and purpose. Without the need for a telemotor, this wheel could serve as a backup in case the hydraulic lines were breached or the telemotor was damaged or destroyed. In fact, many ships had a backup steering system which was directly connected to the steering engines, especially warships where the bridge was likely to get shot away in combat. Because Titanic's third steering wheel was located on top of the docking bridge, where crew would stand to assist Titanic's departure or arrival from port, it was long assumed that this wheel might be used in the docking process, but more recent analysis suggests that the wheel purely functioned as a backup in case the telemotor and hydraulic systems were down. In photographs, the wheel is always either covered up under canvas or just not being used at all. With so many redundancies in place, Titanic's builders had made sure that virtually any conceivable eventuality could be dealt with. But Titanic wasn't just a steel cocoon full of machinery. She had also become home to hundreds and hundreds of temporary residents, the passengers, and an equally impressive amount of permanent ones, her crew, made up of sailors, engineers, stewards, officers, cooks, and many, many more. One of the huge challenges any shipbuilding team must overcome is just how to make the vessel as comfortable as possible, and a big part of that comes down to heating and cooling. Titanic's designers had to turn their attention to a complex array of ventilation systems to make sure that, no matter the climate, all the 3,300 odd people aboard could live in comfort. Now, I already mentioned that the Titanic was essentially a giant steel box. The ship's hull was made of steel frames, clad with steel plating, that was around an inch thick, and although this sounds fairly hefty, it isn't much when you consider on the reverse side of that steel plating is the vast, freezing cold Atlantic Ocean. The design brief Titanic's engineers stuck to was to make Titanic feel, to first and second class passengers at least, like they were staying in a hotel and not a ship. To that end, the ship had to be nice and warm, even in the middle of the coolest Atlantic winter. But it's not just a question of heat. Imagine how stuffy a ship could become without fresh air being circulated through it. The interiors of ships are cavernous spaces, but with 2,200 people living in close proximity to one another, the air could fast become stale and very unpleasant. In the days of old, sailing ships had a real problem with this. Conditions for fare-paying passengers were nothing short of horrendous, with the ship's rotten bilge water permeating the air. Now, to get fresh air into the ship, shipwrights installed these things called cowl vents, and even though you may not be familiar with the name, I'm sure you've seen them before because their shape is iconic. Rounded and kind of L-shaped at the top to prevent rainwater from entering from above, their function was really simple. You could point them into the wind, and their round intake would hopefully pick up some of the fresh air and drive it down into the ship. They were totally unpowered, just relying purely on the strength of the wind, so you can imagine that sitting on a hot night in port without a gust would have been miserable. So Titanic's designers had a few challenges to overcome. First, they had to get good clean air constantly into the ship. Second, they had to heat the ship's spaces to a comfortable temperature. Third, they had to cool some parts of the ship off that naturally ran hotter. And finally, they had to get the stale and hot air out of the ship as quickly as they were pulling in the fresh air. Not entirely easy when your ship's internal volume is around 45,000 gross registered tons and divided into hundreds and hundreds of individual rooms and spaces. Here's how they did it. Titanic used two kinds of system to bring fresh air into the ship, powered and unpowered. Now, you already know that back in the day, ships had cowl vents and the crew would kind of maneuver them and point them in the direction of the wind, hoping to catch fresh air. And interestingly, Titanic had them as well. These were useful for easily getting air into rooms that weren't too far away from the top deck where the cowl vent would be placed. You see these cowl vents at the stern. They drew in fresh air for the third-class general and smoking rooms directly below. You can usually tell which vents are unpowered. They usually had little handles on the sides that you could swing the vents and point them in the direction the wind was blowing. They sat on top of this thing called a coaming and could rotate a full 360 degrees. I can't help but laugh sometimes. I've seen people arguing online about which direction these vents faced and even critiquing people's model kits because they put the vents on the wrong way. But really, they could be posed by the crew in any direction to catch the wind. Titanic was like an 882-foot-long, 10-story building. It needed a lot of fresh air, and the power of the wind just wouldn't cut it. Harland and Wolff, the Titanic's builders, would need some mechanical help to get fresh air into their ship, and they got it in the form of the Scirocco fan. If you've ever looked closely at the photos or paintings of Titanic, like this brilliant piece by Ken Marshall, you've probably seen all these strange-looking objects scattered around the decks. I don't know, I was fascinated by them as a kid, even though I didn't know what they were. And these are vents which were connected to electric fans and drew in huge volumes of fresh air down into the ship. The Scirocco vent was a 19th century refinement of a 16th century invention. The Scirocco is actually a brand name, so called after a Mediterranean wind that originates in the Sahara, and the business was established in Belfast. It uses a kind of fan called a centrifugal fan, different to a ceiling fan you might be used to seeing with blades sticking out from a central point. Instead, it uses an impeller, a kind of wheel with small angled blades. The impeller spins and creates negative pressure, drawing air in and then pushing it along in a totally different direction. In the case of the Scirocco vent, the air could be drawn in through a vent cover and then sent deep down into the ship at a very fast rate. The impeller in the fan was driven by a small electric motor. They were quiet, reliable, and hugely effective. Some Scirocco fans weren't used for drawing air in. They're actually used for extracting foul air from very deep in the ship and pulling it out of the ship itself. Titanic had somewhere around 64 Scirocco vents in a dazzling array of sizes and shapes, and simply put, the bigger the fan, the more air it could draw down into the ship. This was really useful for dictating how big a fan and vent you'd need based on where the air was needed. For example, a small individual galley would only need a single, smaller cowl vent with a tiny fan, but for the larger spaces in the ship, like the dining saloon, the big 35-inch Scirocco fans on the boat deck would be needed to draw in huge amounts of air. In fact, the dining saloon is a really interesting example of a space which needed as much fresh air as it could get. It was all the way down on D-deck, quite large, but with a relatively low ceiling for a room which was intended to seat hundreds of guests for dinner. In photos, you'll notice the ship was festooned with hundreds of lights. Bulbs back then were pretty simple and they ran incredibly hot. The dining saloon on Olympic became notoriously hot at meal times as those lights baked the people sitting under them. There's nothing more uncomfortable to wear than Edwardian formal wear in hot weather. Trust me on that. You can tell it must have been bad because the ships were even fitted with small electric fans to get their air circulating. So to counter this, a few heavy-duty Scirocco fans up on the boat deck and deck houses were used to draw fresh air down and pump it throughout the room. Now the Scirocco fans also drew in fresh air to circulate amongst the passenger cabins. All cabins were reached by trunking, long ducts which were originated at the fans on the boat deck level and, like the roots of a great tree, reached down into the depths of the ship and branched out into individual cabins. First-class staterooms had the vents covered with decorative grills, but down in third class it was a lot more utilitarian. You could see the trunking up on the ceiling where it sat uncovered. Of course, in first and second class, the trunking was usually buried behind wooden panels and decor. Another way of getting fresh air into your stateroom was to simply open your porthole. And to that end, Titanic had thousands of portholes along her side. Most of these swung inwards, so you'd be hoping the wind was pointing in your direction. But the ship also had a few unique types of porthole designed specifically to direct fresh air into the cabin. Of course, these were usually reserved almost exclusively for first class. The Utley Company provided their patented swiveling porthole, which didn't open inwards but swiveled to the side, meaning you could angle the glass itself out to catch the wind and funnel it into your cabin. Remember, Titanic would be moving forward at 22 knots or so. That's 25 miles per hour or 40 kilometer per hour breeze. Not too bad for getting fresh air into your cabin. But probably the most important rooms to get fresh air into were down in the boiler rooms. The men who worked down here had to deal with the heat of their open furnaces, the harsh physical labor involved in shoveling tons of coal, and the tons of acrid coal dust simply kicked up by their activities. It was nasty stuff, and some pretty serious Scirocco firepower was needed. First, the ship's designers installed massive vent intakes called stokehold vents at the base of Titanic's first 3 funnels, one facing forward and one backward. The vent literally ran straight down, like an elevator shaft, into the bottom of the ship. It was a 10-story deep shaft that terminated at the lowest decks, and here they placed the boiler room's secret weapon, Scirocco fans, but not just any Scirocco fan. These were monstrous 55-inch fans which totally dwarfed the largest 35-inch units up on the top decks. 8 of these 55-inch stokehold Scirocco fans serviced the ship's 6 boiler rooms, and they drew in gallons of fresh air on a constant basis. They were driven by electric motors which could output some 30 brake horsepower, and they were also backed up by 2 slightly smaller 50-inch units and a couple of other smaller ones. Because the stokehold vents ran straight into the bowels of the ship, on the night of the sinking, anybody unfortunate enough to be close by would have been drawn against the grating and pinned there as water roared in to flood the empty space inside. This happened to Charles Lightoller, Titanic's second officer. He was dragged underwater and pinned to the stokehold vent intake and couldn't break free. At the very last second, a blast of hot air from below pushed him up off the grate and he was able to swim away. Another simple method of ventilating machine spaces was extracting hot air. Titanic's boilers and steam lines ran at enormously high temperatures into the hundreds of degrees. It meant that the machine rooms and boiler rooms were constantly subjected to hot air. Unfortunately, by its very molecular nature, hot air rises. Titanic's designers harnessed this by installing vast, empty shafts uncovered at the top so that hot air could just rise up and out of the ship on its own. For the boiler rooms, Titanic had these things called fiddly grates installed at the base of the funnels just behind the stokehold intakes. These had a simple metal grate cover on top and ran down into the boiler rooms. They could also double as an emergency escape or access point, and they had ladders which reached all the way down into the boiler rooms from the top decks. The engine room needed a natural vent too. Titanic's designers installed a big skylight deckhouse between funnels 3 and 4 and a shaft that ran all the way down unimpeded into the engine room. This too was covered in gangways and ladders and provided an easy access point for the ship's engineers if they didn't want to go down through the passenger areas. In fact, the engineer's smoking room was attached to the big engine room skylight deck house on the boat deck along with their own little promenade where they could stretch their legs. At the top of the deck house were skylight covers which could be shut totally if the weather was bad, but most of the time they were locked open. in either the full open position like here or propped up in the half open position like this to prevent rain or soot from the funnels from falling in. A lot of lessons had been learned from the Olympics maiden voyage and afterwards, and it was found that there just weren't enough Scirocco vents, and those that were there were just too small to get enough fresh air down into the ship. So on Titanic, these were sized up while she was being finished, and the lessons were implemented. Olympic eventually also got enlarged Scirocco fans during a 1912 and 1913 refits, but the layout and arrangement of these was always changing. By the 1930s, the layout of Olympic's vents was almost unrecognizable to that of a 1911 configuration because they were just getting bigger and more numerous all the time. Now the designers were getting fresh air into their ship, they had to regulate the temperature so passengers would be comfortable, which was no easy task when the outside air could reach just above freezing in winter crossings. Of course, the amount of warm air being drawn into cabins was dictated by class, but not in the way that you'd think. To warm much of the air being drawn into the ship, the designers used these things called thermotanks. The thermotanks were basically giant radiators that used coiled pipes heated by steam to heat the air that was drawn over them by a fan. The air for second and third class was referred to as hot air and was heated by the thermotanks. The fresh air was drawn in with a Scirocco fan over steam pipes within the tank that heated the air up to about 80 degrees Fahrenheit or 27 degrees Celsius. The fan then drew the hot air through trunking and distributed it throughout the ship. The downside to this is that there was no ability to modulate the temperature. So as long as the thermotank was on, the unit was heating the air and supplying a constant stream of 27 degrees Celsius air into the cabins and spaces. For first class though, things were a little bit different. Steam tubes were located within the boiler uptake casings and heated the air only to about 65 degrees Fahrenheit or 18 degrees Celsius, much cooler and more comfortable. Titanic was a British ship, and 65 degrees was considered, for the time, something like room temperature is today. For Americans from states like Florida or Southern Europeans though, this just wouldn't cut it, so plenty of electric space heaters, about 500, were placed around the first class rooms, most notably on the grand staircase here. A few of these space heaters have even been found in the Titanic's debris field, still largely intact. Most people are surprised to learn that all but one of the fireplaces on Titanic were decorative and use electric heaters in place of a fire. The only functioning fireplace on the ship was up in the first class smoking room, and even then, only because it was easy to install a flue and chimney leading directly to the fourth funnel to get rid of the smoke. Now here's a fun little detail. You might have noticed this little decorative brass trim at floor level in rooms like the dining saloon and the smoking room. It wasn't actually decorative. This is a grill vent cover for where the warm, fresh air would enter the room from the boiler casing. Now that the air was being warmed, the designers had to find a way to keep it so within the ship, because believe it or not, bare steel doesn't do a very good job of keeping heat in, especially when the outside temperatures can reach around 3 degrees Celsius. Insulation was used to protect Titanic's first and second class passengers from the freezing cold steel. Third class passengers weren't so lucky, but at least their air was being heated to 80 degrees Fahrenheit. Obviously, the bare steel in the majority of first and second class was clad with timber paneling, but first the builders installed insulation to partly dampen the effects of the outside cold. The insulation ranged from appearing like a fibrous horsehair material to being more like canvas cloth. In other parts of the ship, though, there was a different issue. The Titanic's funnel uptakes reared up high through the ship, right through passenger spaces like cabins and the dining saloon. The uptakes carried the superheated furnace gases and coal smoke up and out of the boilers to the ship's funnels, and they ran hot. Made of steel plating, the uptakes could be up to 300 degrees Celsius or 570 degrees Fahrenheit. Where they crossed into passenger spaces, they were hidden behind bulkheads and paneling, of course, but very heavily insulated with cork. Tons and tons of cork. Without it providing a buffer between the uptakes and the public room walls, the temperature would be unbearable, especially for inside staterooms. Huge slabs of cork, up to 18 inches or 45 centimeters thick, were installed to prevent heat from escaping out. And after the Titanic sank, a huge amount of cork could be seen floating on the surface. The ship had broken up, and it's likely the cork panels were shredded during the sinking and floated free to the surface. The cork was also used in the ship's refrigerators to insulate the cold storage from the room temperature outside. So that's how they did it. I mean, Scirocco fans weren't particularly unique for the time. A lot of other ocean liners like the Lusitania and the Mauretania had used them years before. Because Olympic and Titanic used more powered vents than many other ships at the time, they could boast decks which were relatively uncluttered. Just compare the Titanic's boat deck with that of a German liner, which was just a few years older, where fewer and smaller powered fans were used. It's just another example of the clever engineering that went into construction of what were then the world's greatest ships. Today, many of the Scirocco fans still survive, intact and in place on the wreck, although they won't be there for much longer. But because they're made out of very thin steel, they're being eaten away at, just like the ship itself. With passengers living comfortably aboard, they might have strolled the promenade decks happily, lazing away the days at sea, but all the while walking right past one of the ship's most crucial safety features, the lifeboats. Titanic's boats have become the centre of fierce controversy, and in the wake of the disaster, the number actually installed was heavily scrutinised. At Southampton, before setting off, Titanic's boats had been tested to make sure they could lower safely away in the event of an emergency. There were only 20 of them in total, but the reasons for including such a relatively small number, especially at that time in history, are especially interesting to consider because, although the crew didn't know it yet, they would soon become very, very important. Harland & Wolff, Titanic's builders, had been partnered with White Star Line for decades, since the 1860s, building and launching some of the world's finest ships. By 1909, the companies had introduced ocean liners of dramatically increasing size. In 1899, the company's largest ship was the Oceanic, about 704 feet long and 17,200 gross registered tons, and just 5 years later, in 1904, it was Baltic, almost 24,000 tons and 730 feet long. The size and capacity of ships was just getting bigger and bigger all the time, because then, only 5 years after the introduction of Baltic, White Star Line wanted to construct a trio of liners 45,000 tons and almost 900 feet long. The jump was enormous, and Harland & Wolff knew it. One of the many enduring myths surrounding Harland & Wolff, Titanic's builder, is that they cut costs or somehow skimped out on quality, and it's just not true. They were world-class shipbuilders and immensely proud of their product. That, and they took maritime safety extremely seriously. Any incident or disaster at sea could badly damage their reputation, and major shipping companies might be tempted to place orders for their new ships at one of the dozens of other shipbuilding firms around Britain. Harland & Wolff had to prove time and time again that they were the best. This new trio of 45,000-ton superliners would be an excellent opportunity to prove the fact once again, and every single consideration would be taken. This extended from luxurious fittings and interiors all the way to advanced modern safety features. The new ships would be the absolute best afloat. Contrary to popular belief, the early stages of Titanic's design weren't headed up by Mr. Thomas Andrews. Instead, it was Alexander Carlisle, a veteran naval architect who played a major role in outlining the initial plans for the new ships. Given that the new liners would be double the size of the previous generation of the White Star ships, Carlisle and Harland & Wolff's design team figured that the number of lifeboats would need to increase considerably. And to help plan the lifeboat accommodations, the company turned to Mr. Axel Wellen, a renowned Swedish inventor and industrialist. Wellen had worked with the Royal Navy on breaches for their cannons, but in the early 1900s he sought to solve another problem. See, warships of the early 1900s had also grown considerably in size, and their hulls featured complicated designs that resulted in decks covered in guns and cluttered equipment. Simply put, it was just too hard to get lifeboats, stored high up above the water and far away from the side of the ship, out and over the side. Wellen designed a quadrant davit, which is really a type of crane that could work in pairs to pick up a lifeboat and swing it way out over the side of the ship, where it could be filled with people and lowered away. The benefits of his design didn't end there. The davit arms were so tall that 2 boats could be stacked on top of each other, or a whole second row of boats be stored inboard. His patent, filed in 1907, was approved and adopted. And in keeping with their mantra of using only the most modern technology, Harland & Wolff engaged Wellen to supply the new ships with his fancy new davits, and in May 1910, Wellen weighed in on his proposal for the total number of lifeboats Titanic ought to carry and their placement aboard the ship. All up, Wellen proposed that Titanic carry 32 boats, serviced by 16 pairs of Wellen quadrant davits. 1 row of boats could be kept along the edge of the boat deck with a second set of boats inboard on the deck as well. The exact placement of the boats, according to Wellen, is kind of the subject of some speculation, but if I had to guess, I would assume he would have suggested keeping the boats in 2 groups of 8 on each side of the ship. A group forward where the officers' promenade was, and a group further aft, around about the region of the second-class promenade. 32 large wooden boats would give Olympic and Titanic capacity for about 2,080 people, which was still short of the ship's maximum capacity of about 3,300 people. But hang on a minute, Mike, I can hear you asking, why plan a ship lifeboat capacity for only 3/4 of the total complement? Well, this is actually all partly down to a bit of a wide-ranging philosophical discussion on what a lifeboat is actually for. See, lifeboats at the time were simple, crude, open-topped wooden boats, a little smaller than your average sailing yacht. In any kind of choppy sea, a fully loaded boat would be a perilous proposition. Left to the elements, the occupants would be tossed around and drenched, and more than likely drowned if the boat tipped over. This actually happened fairly frequently. For example, in 1906, the SS Valencia was wrecked on a reef off Vancouver Island. The ship was stranded in sight of the shoreline less than 90 meters away, but against the captain's orders, 6 of the ship's 7 lifeboats were filled and lowered. 3 flipped while being lowered, spilling their occupants into the sea and drowning them. And of the 3 that survived lowering, 2 capsized and 1 just outright disappeared. Only 9 men safely made it to shore. In 1904, the SS Clallam, a small 168-foot-long steamer, ran into trouble in heavy seas and began taking on water. The ship's captain, Roberts, ordered women and children into the 3 lifeboats and lowered them away, but all 3 either tipped during lowering or capsized, and everybody in the boats was taken by the waves and drowned. By contrast, Clallam, ironically, stayed afloat long enough until the next morning, when a tug came to the rescue, and even though the ship eventually capsized and sank, just about all of the 36 people who'd stayed behind and not gone into the lifeboats survived. So history showed that getting into a lifeboat was far from a guarantee for survival. Instead, the emphasis for safety at sea was put into a very different set of safety features, and the lifeboats would serve only as the absolute worst-case scenario if the other 2 features did not work out. The first line of defense was the ocean liner itself. Much greater importance was put on watertight subdivisions and providing ways to seal off damaged parts of the ship's hull to slow or stop the flooding. I've gone into Titanic's watertight compartments in more detail in another video, which you might like to watch, but suffice it to say that the ship was designed to kind of be its own lifeboat. Those recent experiences had showed that lowering away small lifeboats into the vast ocean could just as well be a death sentence for those going into them. Instead, the ship had to stay afloat as long as possible and serve as its own life raft. Even if mortally damaged and ultimately doomed, if the ship could stay afloat for a few hours thanks to the watertight compartments, then rescue was a very real possibility. This was thanks to the second line of defense, the Marconi wireless telegraph system. When it was introduced, this was an absolute game changer in maritime safety. In the past, ships in distress just had to rely on signal flags, cannons, and rockets to hope and pray that another ship might be close enough to see and hear and respond to lend a hand. But by 1909, things had changed dramatically. Many ships now carried the wireless telegraph so they could speak to each other from hundreds of miles away. On top of this, the North Atlantic Ocean was carved into sea lanes, which were basically giant ocean-going highways that meant in any given stretch of the track, there might be up to a half dozen ships within 100 miles of one another. These 2 huge innovations actually changed the reason for being of the lifeboat itself. Before 1900, lifeboats were the absolute last resort, a Hail Mary in case the ship was close enough to shore to attempt a landing. After the introduction of wireless, however, it was assumed that a sinking ship would fire off a distress call only to find multiple ships rushing to its aid. The new watertight measures would keep the ship afloat long enough so passengers would not have to risk their lives in the dicey lifeboat lowering procedure without cause, as on the SS Clallam. Ships arriving on station would stand to, and the lifeboats could then be lowered away, acting as ferries to take loads of passengers from the sinking ship to the rescue ship. To this end, an ocean liner did not need enough lifeboats for all passengers on board because the boats would do multiple trips between the ships and get everybody off safely. It sounded good on paper at least, but in 1909, it was actually proved to be absolutely true. That year, the White Star Line's RMS Republic ran into a fog bank off Nantucket, and she was rammed by the SS Florida. Taking on water quickly, Republic sent a wireless distress signal, becoming the first ship to ever actually do so. Shortly afterward, the Florida, which was actually still afloat, the US Coast Guard cutter Gresham, the RMS Baltic, the RMS Lucania, and the RMS New York all responded and rushed to Republic's aid, arriving on site with enough time to disembark Republic's passengers safely from the ship using its lifeboats. Republic eventually sank, but the only passengers to die did so in the collision and not during the evacuation or after. So with all this in mind, the delicate nature of lifeboats and their susceptibility to the elements, the likelihood of passengers being lost in a panic, as lifeboats are launched, as on the Clallam, Valencia, and many more, against the powerful nature of the Marconi wireless as a safety measure, and the design of modern ships keeping themselves afloat for long enough to facilitate a rescue, as proved by the Republic disaster, White Star Line and Harland and Wolff regarded Welland's plan and made some alterations. Welland had called for 32 lifeboats, stored in 2 rows on the boat deck, but the Board of Trade regulations for the day dictated that a ship above 10,000 gross registered tons needed only carry 16 boats, with a minimum capacity of 5,500 cubic feet. Titanic was not 10,000 tons, but a 45,000-ton ship, but the Board of Trade laws were governed by a ship's volume and size, and not its passenger complement. Given that the regulations required Titanic only need carry 16 boats, and that the recent sinking of the RMS Republic proved that lifeboats were useful only really as a ferry between a stricken ship and its rescue ships, White Star and Harland and Wolff removed Welland's second row of lifeboats, essentially halving the number. Titanic would now carry the 16 wooden lifeboats as dictated by the Board of Trade, but to bolster that number, she would also carry 4 collapsible boats as an additional measure. A move the Board of Trade did not require, and an example of Harland and Wolff and White Star going a step beyond the mere requirements. This decision has been heavily criticised for over a century now, but has also been heavily mythologised. That the decision was made by White Star chairman J. Bruce Ismay because he just didn't want the decks cluttered with all those lifeboats, or that the designers actually wanted 64 boats but were overruled at the last minute. Just none of it is true. Ismay never interfered in the planning of safety measures for his ship. Instead of relying just on lifeboats with their checkered history of botched passenger evacuations, the company would instead rely on new technology. The wireless system and the watertight compartments, which had been proven in 1909 to work well. Titanic could be its own lifeboat, and if it was ever mortally wounded, it would stay afloat long enough to effect a rescue. At last, on April 10th, 1912, Titanic cast off from Southampton's docks and headed out through the Solent for her first stop in Cherbourg. With hundreds happily aboard and excitedly exploring their new temporary home for the first time, the ship's crew got to work housing and feeding them. And stories beneath their feet, dozens of men toiled away to keep the ship's propellers actually moving and to keep Titanic up to speed. The engineering crew were a proud bunch who looked after an incredible array of steam machinery that was among some of the most effective at sea, and they had been built back in Belfast in a special engineering shed that housed some true mechanical marvels. These are the reciprocating engines of Titanic before they were installed in the ship. Here, the workmen of Harland and Wolff are just test-fitting the assembly. The engines were actually installed in pieces with the help of a massive floating crane. When we think of Titanic's power plant, these were probably springs first and foremost to mind. They are towering and incredibly impressive, but they are just one part of a much larger system which, when combined, was able to drive Titanic through the mighty Atlantic Ocean at speed. Today, we'll break down this system and learn how Titanic was powered. We'll look at the boilers where steam was generated. We'll follow the steam on its path, first through the main engines, then into the central turbines, and finally the condensers. And then we'll look at how the sheer power of this whole assembly resulted in turning the massive manganese bronze propellers. We're going to look at some pretty incredible machinery and learn how it all worked. But interestingly, we need to start our journey not with a machine, but with a man. This is Frederick Barrett, then 29, from Southampton, England, and aboard Titanic, he had a special job. Barrett was a fireman, one of nearly 180 men whose job it was to feed Titanic her fuel, and this was no easy job. The firemen were a special bunch, nicknamed the Black Gang because they would return from their shifts coated in thick coal dust. Their job was so demanding and filthy they had to be kept separated from the majority of the rest of the ship's crew forward in the very bow of the ship in big dormitories. To get to work, they would trudge down a winding, long staircase into the very bowels of the ship. Shuffling through a narrow tunnel, they would make their way into their office. This was one of the cavernous boiler rooms. Titanic had 6 of these massive compartments at the very bottom of the ship, running for about 320 feet of the ship's entire length. Their sides were the ship's hull itself, unshielded from the ocean, and about 30 feet or 9 meters below the surface. Up above, narrow catwalks branched out and provided emergency escape pathways up top, But the main event of these rooms were the boilers. Titanic had 29 of these beasts, and this is where the ship's propulsion really began. Titanic was wide enough that in most of the rooms, 5 boilers could be arranged and seated side by side, but towards the bow, as the hull narrowed, the final boiler room could only fit 4. The boiler rooms were numbered 1 through 6, and Boiler Room 1's boilers were different from all the rest. They were only single-ended, meaning they only had 3 furnaces each on one side. The main boilers throughout the other rooms were double-ended with 6 red-hot furnaces, each hungry for tons and tons of coal. The main boilers were 15 feet or 4.5 meters tall, and 20 feet or 6 meters long, massive things that existed purely to burn coal and boil water. The boilers featured corrugated furnace tubes where the coal would be loaded and burned. Running the length of the boilers inside were fire tubes, pipes where the hot gases and exhaust from the furnace would be drawn through. 3/4 of the inside of the boiler was filled with water, and it would be boiled off into Titanic's very lifeblood, its steam. But not just any water could be used. Any impurities could gunk up the machinery and have terrifying consequences. A boiler or steam pipes lined with leftover residue could eventually burst in a scalding explosion. A complex system designed to recirculate water throughout the ship and its engines was employed to keep things as pure as possible. It all started down in the very bottom of the ship. The ship's double bottom was a special safety feature that added a second inner skin to the bottom of the ship. It stood about 5 feet above the keel. Now this inadvertently created a huge amount of enclosed space which designers could use for water storage. The inner spaces of the double bottom were sealed off and segmented into 44 tanks which could hold fresh or salt water for different purposes. Using suctions and an array of pumps, up to 5,754 tons of seawater could be drawn in for ballast to help balance out the ship's trim as it sat in the water. An imbalance could be bad news. Here's a picture of Olympic with a very noticeable lean to one side. Counterflooding the ballast tanks could balance this out and return the ship to an even trim. Aside from these saltwater tanks, there were also 7 freshwater tanks which could hold just under 1,000 tons of water, much of it actually used for drinking water. But Titanic's boilers needed to consume a monumental amount of water to keep generating all that steam for the engines, but salt water couldn't be used. Boiling salt water in huge volumes would create a massive amount of leftover salt, which would block the lines and be catastrophic to the whole system. Commenter Not9873 pointed out that a buildup of any kind of scaling, that is minerals in the water that adhere to surfaces over time, can create additional insulation inside the boiler and lead to a buildup of temperature. Now this can lead to a tube or a pipe burning through, sending all that hot gas and fumes back into the furnace and then venting out under extreme pressure through the boiler and into the crew spaces, and anyone standing around would be horribly scalded. Titanic's boilers used what was called feed water, that is fresh water provided at the start of a voyage by tender. The feed system was ingenious. It was a simple closed loop. The fresh feed water would be boiled in the boilers, turned into steam and then sent through to the main engines, exhausted out, sent through the turbine, cooled and then condensed back into water by the condensers, circulated through filters, back into the boilers to go around again. But over time, as the engines ran for days on end, there would be a natural amount of evaporation or contamination from things like grease or lubricants. The water would need to be topped up, and for this, Titanic's boilers could use seawater to create boiler feed water. It just had to have all of the salt taken out of it first. To do this, Titanic used machines called evaporators to take seawater drawn into the ship and essentially boil the salt right out of it. The evaporators were a kind of heat exchanger. Like the ship's main boilers, they too used a system of tubes, but these tubes were fed by the ship's hot steam. Seawater would come into contact with these extremely hot tubes and boil off into steam, leaving salt deposits behind. And the steam was then cooled, and as it did so, it turned into distilled water. While much of the feed water was condensed and turned into distilled water, a lot more of it was run through the evaporators to remove the excess salt, and then it was dumped overboard. The evaporators could make up to 60 tons of distilled water every day. The distilled water created by the evaporators wasn't used for passenger drinking water. It could, in emergencies, be aerated
and circulated as drinking water, but it was mainly used to feed water into the boiler system. Passenger drinking water was stored down in the tanks of the double bottom. It would be pumped up to the boat deck, where a holding tank in the engine room ventilated deckhouse could rely on gravity and pressure in the water pipes that ran up Titanic's funnels to run directly to the taps throughout the ship.
3/4 of the boiler was constantly filled with boiler feed water, but the top quarter was left empty because this is where the steam would begin to accumulate. As the fire tubes began to heat up, as the hot gases from the furnace were drawn through them, they would heat the water around them until they could turn the water instantly to steam. In fact, so much of the stuff would be generated that the boilers would eventually be under 215 pounds per square inch, or about 15 bar of pressure. All up, the 159 furnaces boasted 144,000 square feet of heating area, a monumental surface area, and every bit of it was needed to feed the hungry, powerful engines. All good fires need air to burn efficiently, and Titanic's boiler furnaces were no different. But being positioned at the very bottom of the ship, this provided a unique challenge for the builders. Some designers opted to use a system called forced draft, where fans would suck air from above directly into the boiler furnaces, but this meant the boiler room itself would go largely unventilated, creating hellish conditions for the workers. Titanic used a different system, a natural draft. 12 huge Scirocco ventilator fans sucked air from the ship's topside deep down into the boiler rooms themselves. It cooled the air somewhat, provided fresh air as well, but then it also fed the boilers. The pressure differences caused by the burning fires and the Titanic's huge funnels up above would force oxygen into the boilers through vents, creating a constant flow of air into the ship's fires. Like the legs of a giant spider, the funnel uptakes branched out and met each boiler, carrying all the excess smoke and dust way up 175 feet or 53 meters up and out the top of the 3 functioning funnels. This is one of the reasons why ships' funnels were so tall at the time. It wasn't just to clear soot and ash away from the ship. A taller funnel would create a greater draft, and the furnaces would burn better. It's why Cunard ships of the time had those massive smokestacks. It wasn't just for show. In Titanic's boiler rooms, fireman Frederick Barrett and his colleagues would work around the clock in shifts. In fact, their work was so hard that they would work 4 hours on and then have 8 hours off duty. And that's for good reason, because in the stokehold, the working spaces of the boiler rooms could reach 49 degrees Celsius or 120 Fahrenheit. All that despite the air being sucked in by those big Scirocco fans. The firemen would shovel coal into the boilers to keep the furnaces burning bright and the steam pressure at the desired level. And this was communicated from the bridge via illuminated panels, which would order the boilers to stop or provide pressure enough for slow, half, or full speed. At full speed, Titanic would burn through up to 600 tons of coal per day. That's the weight of 2 London buses worth of coal per hour, and all of it was shoveled into the furnaces by hand. There was so much of the stuff being consumed that as the coal levels dropped, it was the jobs of trimmers to make sure that the ship wouldn't be off balance as the coal bunkers, or the storage, were depleted. So with Barrett and his fellow firemen working in the boiler rooms, ensuring constant pressure and a consistent burn, the steam would be vented under pressure into the engines. It was fed into 2 main steam pipes of heavy rolled steel. The pipes ran from the boilers back along the ship's length towards the engine room compartment. They passed through watertight bulkheads, coal bunkers, and boiler rooms until finally they met the engine room. And this is where the steam that they carried was put to its first good use. The main engine room was a cavernous space almost 70 feet or 21 meters long, occupying the entirety of a watertight compartment and the entire width of the ship. Early on, when Titanic had been newly launched and the room was empty, the room would have seemed like the inside of a massive steel cathedral. It soared all the way up to D-Deck, but once the engines and auxiliary machines had been installed, the space would have been entirely occupied by their massive bulk. The engineers basically lived and worked almost inside their engines, using catwalks and ladders to nimbly maneuver between the massive pistons and bed plates and keep the engines turning efficiently. Titanic actually made use of a weird, hybrid form of propulsion. Shipbuilders of the time had 2 main engine types to choose from. The newer turbines, which were extremely powerful, but they were somewhat expensive to run. Early Parsons turbines weren't geared, so they consumed a massive amount of fuel. Not only that, but being the newer technology, many shipbuilders didn't trust them yet. By contrast, builders could employ the older triple or quadruple expansion steam engines. These were cheaper, reliable, and more economic, but they were slower and would mean that your ship was not liable to win out the coveted blue ribbon, which was the speed record. Harland and Wolff, Titanic's builders, and the White Star Line, her owners, weren't going for a speed record with the ship or her sister Olympic, but they were also building the largest passenger ships yet built. A pair of triple expansion steam engines alone just wouldn't cut it. Olympic and Titanic would probably only be able to lumber along at 17 or 18 knots top speed. No, a third engine would be needed. A powerful one. And for this, Harland and Wolff chose to employ the sheer brute force of a turbine engine. In this way, the ship would have a kind of hybrid propulsion, squeezing every bit of power that they could out of the steam before it was finished with. But first, it had to go through the ship's twin main reciprocating engines, and these things were truly incredible. The triple expansion steam engine was a monument of Victorian engineering. They'd first appeared in the second half of the 1800s, and they revolutionised ocean-going travel. Titanic's engines were some of the largest ever constructed. The engines themselves were 3 stories tall. They can be a little bit hard to decipher, so I'm going to show you these plans and then explain just the major components. First of all, the engines were seated on huge, heavy bed plates. The engines had to, of course, be fixed to the ship, but this presented unique challenges. For one, operating at full clip, the engines would be vibrating away, and in the worst Atlantic storms, Titanic would be rocking and rolling side to side by as much as 20 degrees or so. The engines had to stay attached with absolutely no risk of falling over. This was not an easy task when those engines weighed 720 tons each. To this end, the engine bed plates were made extremely heavy duty. They were constructed of 5 enormously thick iron castings bolted together, weighing almost 200 tons alone when assembled. These bed plates are from Titanic's sister ship Britannic, and you can see just how heavily constructed they are. It's testament to the engineering and durability of these castings that even through the violence of Titanic's sinking, when the stern was lifted up to 30 degrees into the air and the entire ship's middle disintegrated, the engines largely remained locked in place and are standing on the wreck today. In a way, the bed plates are still doing their jobs 110 years later. Attached to the bed plates were the 4-cylinder support columns in a kind of inverted Y shape, 21 tons each of cast steel. Atop each of these were the massive engine cylinders, up to 50 tons each. No wonder those support columns had to be so heavy duty, and here the name of the engine type might be a little bit misleading because although these were triple expansion steam engines, they used 4 cylinders. Like the engine in your car, these cylinders each had a huge piston attached with connecting rods to the crankshaft. Titanic's engines were double-acting. It was a simple arrangement. Turning the engine would operate a slide valve which, as it went up and down, would admit steam under pressure either at the bottom of the stroke, sending the piston up, or at the top of the stroke, sending the piston back down again. This would happen over and over again, creating an immensely powerful and efficient engine. The engines were called triple expansion steam engines because they would expand the steam 3 different times throughout the 4 cylinders. To run the engines and the turbines, the steam produced by the boilers had to be at a fairly high pressure. On Titanic, it would enter the first cylinder at 210 pounds per square inch. Titanic steam is what we call saturated steam. This was used in machinery throughout the early years of the 20th century. Essentially, it's steam derived from water heated to a specific temperature for a required pressure, in Titanic's case about 215 pounds per square inch. But saturated steam, like that used on Titanic, contained minute droplets of water. As soon as it goes through the system, it naturally condenses a little bit as the heat is lost, losing steam volume and pressure. For example, Titanic's boilers created steam at 215 pounds per square inch, but it reached the engines at 5 pounds per square inch less. As it dropped in temperature, it would naturally condense and create water droplets. So to deal with this, Titanic's steam lines featured separators which were designed to catch water droplets and remove them before the steam entered the main engine cylinders. It would come from the big main steam lines from the boilers and enter the high pressure cylinder at about 210 pounds per square inch. It would be exhausted here and then vented into the next cylinder, the intermediate pressure cylinder, designed to operate at 78 pounds per square inch. Again, it would be exhausted down to 24 pounds per square inch in the low pressure cylinders. Counter to what might seem like common sense, the first cylinder forward was actually a low pressure cylinder. This was implemented as a way of balancing the engine and reducing vibration. In this way, the steam was vented through, lifting all 4 pistons, turning the crankshaft, and being exhausted of most of its pressure. The triple expansion engine's secret to success was the fact that it could capture the power of the steam from 210 pounds per square inch gauge all the way down to 24 pounds per square inch gauge before exiting totally exhausted at 9 pounds per square inch absolute, which is actually below the pressure of Earth's atmosphere. The engines could be worked up to full speed over the course of about an hour, and to reverse direction they needed their own dedicated Brown's reversing engine to engage the cranks and reverse the rotation on the crankshaft almost immediately. To control the engine's speed, valves could bleed off steam to ensure the right amount of engine revolutions was being met. At full steam ahead, this was about 75 revolutions per minute, but when manoeuvring around port, it would need to be much slower. The engineers could use the bypass valves to bleed off pressure and accurately follow orders from the bridge, which was sent down via telegraphs. All told, the 4 cylinders of the engines could generate 15,000 horsepower as they used the steam at all 3 levels of pressure. Scattered around the engine room were the bits of miscellaneous machinery required to make all of this happen. Feed pumps, air pumps, direct contact heaters. It was a dazzling, cramped space, but to the ship's 60-odd engineers and greasers, it was home. They would have known its baffling layout like the back of their hand. On the 6-day voyage from Southampton to New York, the engines would need to turn well over 500,000 times. And to keep it all working efficiently, engineers worked around the clock and watched the pressure levels and revolutions carefully. The greasers were employed purely to ensure the massive connecting rods and crankshafts were properly oiled and lubricated so they could keep working non-stop for the entire voyage. The steam, once it reached Titanic's engines, would have been hundreds of degrees in temperature, and the engine room would have been extremely hot, were it not for a clever bit of simple engineering. Towering over the engine room was a skylight way up on Titanic's boat deck with covers which could be swung open. Not only did this admit natural light deep down into the engine room's depths, but it made use of a simple principle of thermodynamics. Hot air rises. It meant that without assistance, the heated air generated from the steam in the engines would rise up and out of the skylight. But for now, we need to step outside the confines of the engine room and look further back at the very stern of the ship, because here, either side, were the 2 massive outboard propellers. These beauties combined a steel hub with bronze blades in a massively heavy arrangement. They each weighed about 38 tons. To actually get these monsters to turn and cut through the water at speed, the main engines needed to transmit their power, but they were far away, about 250 feet further forward. To actually connect the engines to the propellers, huge long propeller shaft assemblies were needed. The propeller shafts were made up of steel cylinders about 30 feet long that tapered gradually away from the engines and out into the outboard propeller wings, where they met and connected to the propellers. These would be constantly revolving, so they were housed in long tunnels where crew would have access for maintenance, the shaft tunnels, and they had forced lubrication systems to ensure there was no friction buildup and the propeller shafts could continue turning non-stop. But there was a huge engineering challenge thanks to the propellers themselves. The ship's thrust forward or backward was transmitted along the propeller shaft from the propellers, but the resulting force would be fatal to the engines. They weren't designed to absorb that massive force or the resulting vibration. Instead, special devices had to be built that would take all that power from the propellers and transfer it away from the engines and into the very hull of Titanic itself. These were the thrust blocks, and their function was simple in concept. The propeller shaft exiting the engine was connected directly to the thrust block, a heavy cast iron bed plate mounted firmly to the ship's bottom. A series of 14 collars mounted directly to the shaft here would sit inside a dedicated thrust bearing or shoe. In this way, the thrust coming back from the propellers would be captured by the thrust block and then distributed back into the hull, instead of heading right back into the engines and taking them apart. The engines would turn the crankshafts, and the crankshafts would spin the entire propeller shaft assembly. the thrust shaft and the thrust blocks, then the intermediate and tail shaft assembly, and then finally the propellers. Titanic would be moving ahead. So we followed the steam through the main engines and see how this turned the big propellers. But Titanic's designers had introduced one final ingenious use for the steam before it was all used up. Remember when I mentioned that Titanic employed a weird kind of hybrid propulsion? Well, it was here that the steam was used one last time. Exiting the main engines at 9 pounds per square inch, below Earth's atmospheric pressure, it would be vented into Titanic's secret weapon, the low pressure turbine. Aft of, or behind, the main engine room was the turbine room, a continuation of the engine room space, but separated from it by a watertight bulkhead. Here, the compartment was completely taken up by the enormous turbine, the second largest of its kind ever built. In fact, the biggest low-pressure exhaust turbine ever built went to Britannic, which was Titanic's younger sister ship. The turbine assembly was by itself over 410 tons. It was 50 feet long, longer than a modern Greyhound bus. It was relatively simple in its layout. A huge iron casing was cast in 2 halves. For extra strength, it was heavily reinforced with ribbing. To even cast something as large as this, complicated wooden patterns were made to create the molds. And it was all done in-house. Harland & Wolff's shipyard was a wonderland of warehouses and machine shops where almost every part of the hundreds and hundreds of thousands of individual components used to create a big ocean liner were made by specialist craftsmen. It took just as much attention to detail and care to carve the panels for the first-class spacers as it did to cast the monstrous machinery. But even so, some parts were beyond Harland & Wolff's capabilities. They outsourced even bigger castings, like the stem of the ship, which is the very, very front and back, to the Darlington Forge Company, who specialised in that kind of thing. But at Harland & Wolff, they were hard at work, casting the biggest ever low-pressure exhaust turbine casing. And inside the casing sat a rotor, itself over 100 tons, and spun on a monstrous lathe. The lathe cut grooves into the rotor's body, where thousands and thousands of blades could be fitted. The entire assembly was test-fitted, and then, after Titanic had been launched, it was lowered into the ship from the giant floating crane. In fact, all the machinery fittings were installed after launch. These photos are from Britannic's fitting out, and they show just this. Here are the main engine bed plates, and here are the engine support columns. The basic principle of the low-pressure turbine was that as the steam was exhausted down to 9 pounds per square inch by the main engines, it was vented at speed into the turbine, passing through the casing between the rows of blades. This would cause the rotor to spin, and like the main engines, it was connected to its own dedicated shaft and thrust block, with a shaft leading to the third central propeller, which sat perfectly between the 2 wing propellers. The thrust block for the turbine was different to the others because it was part of the turbine casing itself. All up, the turbine could generate 16,000 shaft horsepower. The benefit of having an outer casing in 2 halves like this was that, for maintenance, it could be cracked open and lifted up with chains by an electric motor and a system of pulleys and eyelets on the turbine room's roof. The secret to the turbine's success was that it could operate with steam venting through that was at pressures below Earth's atmosphere.
Contemporary graphs and information from the age show that in the triple expansion steam engines of the time, 33% of the power extracted from the steam was done so in conditions below Earth's atmospheric pressure. The turbine, running at a pressure below Earth's atmosphere pressure, would actually assist the main engines. It would draw steam through the main engine cylinder, greatly increasing efficiency and power. The whole engine system was connected. The condensers themselves, at the end of the system, operated in a vacuum, 28 inches of mercury vacuum, created by the cooling of the steam itself. As the steam condenses, both its temperature and volume decrease, which in turn cause the pressure within the condenser to drop. Titanic also employed huge pumps to service the condensers, removing condensate from the steam and maintaining that vacuum. On ships like this, the power of the pumps and the vacuum in the condenser unit is such that running the pumps could turn the engines on vacuum alone.
But the central turbine had a couple of quirks. For one thing, it required the main engines to be operating in order to begin capturing the power of the steam as it came through the engines. Crucially though, it couldn't be operated in reverse. No gearing was provided for reversing the thrust, and the rotor's blades couldn't be reversed either. It didn't have a particularly negative impact on Titanic's maneuverability though. There's a bit of a myth that Titanic handled or turned badly, but it's not true. She was a good turner for a ship of her size, but not only that, she was quick. That central turbine was the ace up Titanic's sleeve. It gave her and her sister Olympic a top speed of 23 knots. This was an enormous achievement. Cunard Line's sisters, Lusitania and Mauretania, had been built specifically with speed in mind, and they accomplished this with raw power. 4 hugely powerful turbines outputting nearly 70,000 horsepower. But Olympic and Titanic were 10,000 tons larger than the Cunard ships, but they burned 73% less coal and were, after all that, only 2 or 3 knots slower. Lusitania burned 1,000 tons of coal per day at least, but Titanic, the much larger ship, only burned 600. You can see just how clever the hybrid propulsion engine system was that Harland & Wolff had chose to use on Olympic and Titanic. It was simply engineering genius. There was another clever use of the ship's architecture to keep temperatures comfortable for the engineering staff. We saw how Titanic's main engine room had a large skylight to help hot air rise up and out of the ship. Well, so did the turbine room, and not just any skylight. Titanic's 4th funnel sat directly on top of the turbine room. It didn't vent smoke out of any of the boilers, but it did provide a huge, towering shaft for the hot air in the turbine room to escape. Not only that, but it was crisscrossed inside with access ladders so that engineers on break could climb all the way up and get a breather at the very top of the ship's 4th funnel. Of course, the end result was that all that power was provided to the propellers. The massive outboard props 23 feet across, and the smaller central propeller driven by the turbine about 17 feet across. But here there was an opportunity for Harland & Wolff to squeeze yet more power out of their design. The sheer strength of a ship's engines is useless if paired with a poor propeller design, and back then, in an era without advanced computer modelling and simulations, the only way to properly test was to put new designs into service and await reports from the ship's engineers. For designers, it was all a battle between power and efficiency versus vibration. The number of the propeller blades on the propeller, their angles, their size, their shape, it all impacted how Titanic and ships like her would operate, and until recently, it wasn't known that Titanic was actually experimenting with a different kind of propeller. See, no photos of Titanic's propellers exist. This very famous shot is of Olympic in 1911, and this one, often billed as Titanic in books, is again Olympic but in the 1920s. We know from these photos and engineering records that Olympic, the first of the trio, was fitted with a 4-bladed central propeller. But a recent examination of documents shows the Titanic was likely fitted instead with a 3-bladed one. This was classic Harland & Wolff, experimenting with what would create the most efficient setup while dampening the most vibration. Lusitania and Mauretania and dozens of other ships had their propellers changed quite a few times throughout their careers as new arrangements were tested. Of course, the results of Titanic's testing with the 3-bladed propeller were lost when the ship sank, but after she did, Olympic was also fitted with a 3-bladed setup, and those results were disappointing. She went back to a 4-bladed central propeller shortly after, and that was the end of that. With the boilers roaring red-hot with flame, the reciprocating engines thundering, the turbine whining and the propellers churning the ocean into a whitewash, Titanic would have been forging ahead, her machinery plant working like a beautiful, harmonic mechanical ecosystem. By the time the steam had finally passed through the turbine though, it had finally been exhausted of all of its use for the ship. Coming out of the turbines at a grand total of 1 pound per square inch, it needed to be disposed of. Here, 2 massive condenser units were put to work. These things were pear-shaped and worked in conjunction with a series of pumps and filters to essentially cool the steam back down and convert it again into water. This whole arrangement was extremely simple in its concept, but complicated in its operation. Tubes in the condenser circulated cold water, pumped from the ocean itself, or from Titanic's own bilge tanks. This water then cooled the steam and turned it back into water as well, 700,000 pounds per hour of the stuff, which would then drain thanks to huge pumps into tanks for recirculation through the system or for discharging over the side. The water was passed through filters which took out any impurities, like engineering grease, lubricants and that kind of thing, and then sent right back to the boilers to be turned into steam and sent around again. The water that had been drawn through the main condenser unit that was used to cool the steam was discharged out over the side of the ship in a large cascade through 2 outlets. You can actually see them in the photos of Titanic. It's like a constant stream of water as the ship's main condensers did their thing. On the night of the sinking, this presented a unique challenge. Exhaust condenser feed water, either from the engine's main condenser units described in this video, or from other smaller auxiliary condensers used to service steam-driven machines like pumps, it was all being vented out of the side of the ship right near the waterline. On the starboard side, Lifeboat 13's occupants were surprised to be lowered directly in line with a small waterfall of discharged condenser water. Not only did this almost flood their boat, but then it swept them away directly into the path of Lifeboat 15, which was almost lowered onto their heads. This video has outlined how Titanic's engines worked, but the truth is, it's just a light summary. This speaks nothing of the hundreds of pieces of auxiliary machinery and special devices needed to keep everything running. Pumps, water filters, electric motors and winches, evaporators, boilers, heaters, coolers, hydraulic machines, valves. It was a complicated mass of machinery that was, for its time, the most advanced system in the world. But today, all of it rests at the bottom of the Atlantic Ocean, much of it still in place on the ship. It's an eternal monument to the human minds that dreamt these machines up, the human hands that turned the plans into cold, hard reality, and the human lives spent and lost running them from Titanic's triumphant debut until her bitter end. With Titanic thundering along its speed, the propellers churning the water into a violent white mess behind her, the great ship was at last in the open ocean, headed for New York. She had safely navigated some tricky waterways, threading her way through the Solent, where Olympic had been rammed by a British cruiser, and happily manoeuvring through the shallow waters off Cherbourg and Queenstown. But now, for the officers and crew responsible for the ship's safety, the job was only just beginning, because they would have to keep their ship on course with no land in sight. Since the days of sail, navigators had struggled to find their exact position, often with dire consequences. After all, just how does one calculate their exact location in the middle of the ocean? Titanic relied on some impressive technology for the Edwardian age, but it may surprise you to know that many of the techniques actually used to navigate Titanic were relatively simple and have been in use for many hundreds of years already. The Titanic was designed to get across the Atlantic Ocean in a reliable, dependable way. See, it was a lot like getting a flight nowadays. You'd need to know your exact arrival day and times so that your friends could meet you, or you could organise taxis or pickups at the other end. Not only that, but many passengers had connecting trains or even other voyages on other ships to catch. Being delayed or even arriving early could be a massive hassle. Reliability was key. But herein lies a huge problem. Stretching between Titanic's departure point in Europe and its intended destination was some 5,500 kilometers or 3,400 miles of open ocean. And not just any ocean. This was the North Atlantic, some of the globe's most fearsome waters. Believe it or not, for all of Titanic's size and splendor, it would still have to deal with the same issues that had plagued sailing ships from centuries before Titanic was even dreamt of. Back then, ships were at sea for weeks or months, with no sight of land, no satellite navigation to guide them. How could they be sure of where they were? A compass could point you in the right direction, hopefully, if it wasn't being thrown off by magnetic interference, and we'll get into that in a minute. But after weeks or months being tossed around in the ocean, how could you ever hope to know where you were? Or at least, where you were meant to be going? But Titanic had to overcome those same issues. It had to reliably arrive off Nantucket within just a tiny margin of accuracy. Any further north and the ship might run afoul of Massachusetts coastline. A bit further south, she might run straight into a remote stretch of New Jersey's coast. Fortunately for the crew and officers of Titanic by 1912, there were a few different techniques and technologies that helped in navigating the ship, and some were surprisingly basic. And steaming out of harbour, the first and most obvious thing to establish for your ship was the direction that you were actually heading in, and that required a compass. Back in the day, ships might have carried only one, but Titanic needed redundancies. In fact, the ship was all about inbuilt fail-safes and backups. She didn't have one compass, she had 4. The first two were mounted in the bridge and the inbuilt wheelhouse where the ship was steered from. A third was mounted way back on the docking bridge. This was essentially an emergency steering platform where the ship could be controlled, say, if the main bridge had been put out of action by a rogue wave. Obviously, it would need its own compass, but there were problems with these. They relied on the Earth's natural magnetic field to point toward north, but because it was made of steel, Titanic had its own magnetic field. This meant the compass's needle might be thrown off, and even just 1 or 2 points of inaccuracy could be disastrous, sending the ship totally off in the wrong direction. To counter this, Titanic's bridge was actually made mostly of wood. In photos of the ship's construction, you can even see that the steel part of the ship's superstructure has been built, but a gap has been left for where they'd build the wooden bridge front later on. Despite this, the deck plates directly underneath were still made of metal, and inaccuracies could creep in. Obviously, having 3 compasses was useful. They could be checked and compared against one another, and in extreme cases where all 3 were showing different readings, the average might be taken between them. But Titanic had a 4th compass, and this was arguably the most important. It was mounted high on a wooden platform between the ship's 2nd and 3rd funnel, and what was essentially the very center of the ship. And being raised above the metal deck plates and exactly between the 2 funnels made this also the most neutral magnetic point on the ship. This compass was by its very nature the most accurate of the lot, and all the others could then have their readings compared against it. Knowing what direction they were sailing in was a good start, but how did Titanic's officers know where they were over the course of their 5-day voyage? Inside of land, taking a bearing on landmarks and locations could give your ship's position on the map. The direction that another object might be from your ship is called a bearing. This was measured as a circle with a full 360 degrees. For example, a castle spotted on a shoreline off the starboard bow might be at a bearing of 010 degrees. When they weren't too far from the shoreline, a couple of landmarks could be spotted, and then taking different bearings from these could triangulate or yield your exact position on the chart. To calculate this with some degree of accuracy, Titanic's officers could use a polaris. It's essentially the kind of compass without a needle. Outside of the bridge, on the wings, Titanic had 2 wooden pedestals. The polaris itself was just a portable device in a box, and Titanic's crew could mount it in place to take their readings. Comparing readings against the ship's compass heading would yield accurate bearings on the ship's location. Once land had been left behind though, the polaris was of little use for navigation, but it could still be used to get a bearing on any approaching ships or obstacles at sea. After a day or so into the voyage, there would be nothing around Titanic but open ocean, roaring waves, and an endless horizon. The system used for navigating accurately out there was complex and had been honed after centuries of experience at sea. It is honestly amazing. And it all started with the chronometer, a ship's clock that had to be as accurate as humanly possible. You might be wondering why a clock would be useful in determining where a ship is in the middle of the Atlantic. Well, this all stemmed from an ages-old question that seafarers had been dealing with since the days of sail. The world's maps were divided into a series of geographical coordinates, latitude and longitude. The latitude split the globe across its width, and the longitude from its top to its bottom. Comparing any latitude and longitude would give your exact location on the globe with great accuracy. But there was an issue. At sea, it was easier to determine your latitude, there were simple tables for that, but to determine their longitude, navigators had to compare the time aboard their ship with the time at the agreed 0 point. For centuries, this was done by observing the sun, moon, and stars, a process called celestial observation. The relative positions in the sky at different times of year could give you an accurate longitude. But if there was no moon, sun, and stars, say in a storm that might last for days, you couldn't take a reading. This had been the cause of death for many ships. In 1845, the immigrant sailing ship Cataraqui had been driven directly into jagged rocks off the Australian coast after days spent lost in a storm when the captain and crew couldn't take any celestial readings. 400 died, and only 9 survived the wreck. By the late 1800s though, mechanical clocks had got to a very advanced state of accuracy. Ships were fitted with advanced chronometers in heavily reinforced cases protected from any humidity or temperature changes that might impact the workings inside. Titanic carried 2 chronometers. The second was, of course, a redundancy. Of course, the 2 could be compared against one another to see how accurate they were, and as with the compasses, if there was any discrepancy, an average between the 2 might be used. The ship's chronometers were treated as a sacred item. In port, they were sent to specialist opticians to ensure their accuracy and calibration. At sea, they were religiously wound every 24 hours, even though, with their spring-driven power reserve, they could run for 5 days. Thanks to the chronometers aboard ship, Titanic could time the crew's celestial observations and the amount of time the ship had been at sea with enormous precision. Combining this data with the latitude would give Titanic's position on the globe with a great degree of accuracy. Of course, another relatively simple way of plotting Titanic's position at sea revolved around the sun, the moon, and the stars. Celestial observations were an ages-old way of figuring out where you were. As always, by comparing 3 or more celestial bodies, you could triangulate your position. This wasn't much good at daytime though, because only the sun would be visible. A sextant could be used to take readings of the positions of stars at night and compare them against one another, and use the different data points to triangulate a position on the chart. You'd take a reading of 2 or 3 stars for latitude, and 2 or 3 for longitude, and then use that to find your position. On the night of the sinking, Officer Joseph Boxall quickly took a reading of the stars to work out where Titanic was to call for help. But unfortunately, he may have taken his reading a bit too quickly. He made a slight error, which translated to a difference of some 13 miles or 21 kilometers west of the actual sinking location. But as it happened, this was accurate enough that an approaching ship would be able to spot Titanic's masthead light. When the rescue ship Carpathia arrived on scene, her captain Arthur Rostron congratulated Boxall on his accurate coordinates. With the officers confident they knew where they were at sea, another navigational requirement arose: the need to track progress over the course of the voyage. This was a constant source of conversation among passengers and even a subject of gambling. The daily run was posted every morning and showed how many miles the Titanic had covered the previous day. This could be done from taking measurements on the chart, but Titanic was also fitted with another curious device to measure its speed. The patent log was a simple enough machine designed to measure Titanic's speed through the water and the amount of distance it had covered. It was mounted at the very stern of the ship and essentially comprised a simple rotator, which was similar to a ship's propeller. It was cast over the side and attached to a box with a long cord. It was towed behind Titanic and would rotate through the water at different speeds depending on how fast the ship was going. A series of gears drove dials which registered how far had been travelled in miles according to the rotator in the water. A register up on the docking bridge at the stern of the ship showed the readings. While Titanic was at sea, it was always towing the log behind it, and the readings were checked every 2 hours by a quartermaster on duty. With the voyage coming to an end, Titanic would be again close to shore, so extra navigational care would need to be taken. Thanks to the accurate navigation readings that had been taken at sea, the ship would arrive off Nantucket Island with no trouble. Land could be sighted and the sextant used to calculate the distance from land, and a course plotted to take Titanic up the Hudson and into New York. But if it was foggy, there might be serious problems. Fog at sea, especially off Nantucket, can be a killer. It was responsible for the sinking of Andrea Doria in 1956 when she was rammed by the liner Stockholm in a thick mist. In Titanic's day, ships didn't just have to deal with each other. In a dense bank of fog, an unwitting captain might run his ship directly into the shore without ever sighting land. Buoys were positioned around, as well as foghorn stations which could blast a warning out over the waves. But the crew of Titanic might be confused. The fog could distort the sound and make it sound like it was coming from multiple directions. For this, the Titanic was fitted with what is probably its most unusual and little-known feature: a submarine signaller. If the ship was caught out in a fog bank, it might rely on special buoys that were designed in the 1800s to help out. These had underwater bells. Sound travels much, much further underwater than it does through the air. On either side of Titanic's hull, forward at about the cargo hold, was fitted a signaller, essentially a big microphone built into a tank in the ship's side below the waterline that was designed to detect the sound of those bells. Titanic could hear those bells up to 15 miles or 24 kilometers away. The signallers were connected to a headset on the bridge with a simple telephone cable. And just like a telephone, an officer could pick up the headset and tune in to either the left or the right signaller. Its function was really simple. If you could hear the bells from the left signaller, it meant that there was danger off to the ship's left. If you could hear the right signaller, it meant the same thing for the starboard side. And if you could hear the bells in both signallers, it meant that danger was right ahead. Finally, as Titanic approached the end of her voyage, she might be entering some tricky waterways. Travelling into harbours, the ship would need to stick closely to deep channels, or else she could get beached and stuck in shallow water. To do this, the ship needed a machine designed to register the depth below the ship's keel and ensure that there was always enough of a gap to prevent disaster. Back in the old days of sail, a sailor would literally throw a lead weight on a rope over the side of the ship and figure the depth from how far the line ran before the weight hit the bottom. Titanic took this simple concept and scaled it up. On either side of the ship's bridge was fitted a 30-foot long pole called a sounding spar, which could be swung out over the side of the ship. Then, a heavy metal sinker attached to a cable could be dropped overboard. Readings could be taken with the help of a device called the Lord Kelvin's motorized sounding machine, which was kept on the boat deck just behind the bridge in a watertight case. The cable could run for 600 feet or 182 meters, and attached to the end, as well as the sinker, was a cylinder, which used differences in air pressure to take a depth sounding and record the result. There was a backup for this too. I told you, Titanic, like all ships, was designed with redundancies in mind. Absolutely everything had a backup. On A deck, at either side of the ship, was a small platform that could be dropped and secured in place. Just like on the sailing ships of old, a sailor could cast a weighted line himself over the side of the ship and count out how far the cable ran, and how deep the water was. Setting up and using the sounding machine took time, but if the ship's captain had to feel his way through unfamiliar waters, a sailor out on the leadsman's platform could take regular soundings of depth to give accurate, frequent reports. When they weren't in use, the platforms were folded up and locked to the side of the ship. You can see them appear in photos as a small dark square on the ship's white superstructure. In future years, ships would gain new and innovative ways of navigating with certainty, from wireless radio triangulation and direction finding to radar and, finally, real-time GPS and satellite data. It seems amazing that a ship as relatively modern as Titanic mostly relied on those ages-old means of navigation, reading the stars and sky and keeping track of time. Of course, due to her short service life, Titanic barely got to use many of the devices and techniques we talked about today. Back then, with no radar, navigational hazards mid-ocean were rare, but very dangerous. Icebergs were well known and much feared by sea captains, but there was simply no way of detecting them ahead of time. You could only post more lookouts, men with keenly trained eyes to look ahead in the dark and hope that they'd see ice in time to stop or turn. Now, all of that technology, all of that careful forethought and consideration lies rotting and rusting at the bottom of the ocean. I said at the start of this video that humans have always been the underdog in the story of life at sea, and it's true. Thousands and thousands of lives have been lost, all in the name of simply trying to get somewhere safely, to see loved ones again, to start new lives in foreign places. The ocean has acted as a near impenetrable barrier for countless generations of humanity. You, watching this video, your ancestors once had to brave the oceans in a rickety ship and just hope for the best. Today, we have even greater technology, and ships have become almost inconceivably safe. We still can never become complacent, because with hindsight, we know what happens when complacency slips in. But can you really blame Titanic's builders, her proud owners, and her excited passengers for thinking, if just for a fleeting moment, that at last we had triumphed? That humans were no longer the underdog in a tale that had seen us kicked down again and again in the quest for safer travel. Titanic is a gravesite for hundreds of people, but she's also where an idea went to die. An idea from a simpler, less cynical time, when people really did think that anything was possible. That's why we'll always be drawn to her story. Her sinking is, in many ways, a blow to all of us who dare to dream and design and plan. Many things are just outside of our control, and in some cases will always be the underdog. But if Titanic is a reminder of that uncomfortable fact, then she's also a tribute to those daredevils and those dreamers who tried to reach for the stars to achieve something incredible. And no more obvious is the magnitude of their technological accomplishment than when we pause to learn about how the great ocean liner actually worked.